Hi, my name is Dr. Sean McBride. I'm an assistant professor in the physics department here at Marshall University. This is Jackie Sizemore. She is a graduate student here in the physics department. And she is also the president of our Society of Physics Students here at Marshall. So I'm the advisor for that club as well. So we like to do a lot of outreach with the community, and we've done demo shows for elementary schools and things like that. If you're a student that loves to figure out how the world works around them, I encourage you to come talk to me, call my office, shoot me an email. All my contact information is up on the website for physics. That's mcbrides@marshall.edu. I can give you some information about our program. You'll get a nice Marshall bag here with all the information about our program. We actually have 5 different physics tracks. For those interested in physics and chemistry, physics and biology, medical physics, as well as a new area of emphasis on medical imaging. So with that, let's do some cool science. Right, so this is my favorite demo for introducing students to what physics is. It's based on classical mechanics. It's based on the knowledge of how a pendulum moves. So it turns out that the length of time it takes for a pendulum to swing back and forth from here all the way back again only depends on the length of the string. So I'm going to move this guy so that it's right pointed at the camera as best as I can. And I'm going to set this into motion. Now I know the length of each string, so I'm able to predict this motion. So if we watch the motion of these guys, I can tell you that at 10 seconds, there's going to be 3 at a maximum on each side. So when I say maximum, that means a maximum amplitude. At 15 seconds, there'll be 4 at a maximum on each side. Now something very special happens at 20 seconds. At 20 seconds, they will all line up into 3 rows. And then at 30 seconds, they will all snake apart into 2 separate rows. So you can see them starting to snake apart. Right about there is probably 30 seconds. So this is all predictable by physics and understanding how a pendulum works. So that's an example of classical mechanics. We're going to do some other demos here shortly. So here is an example of electricity and magnetism. So we talked about classical mechanics with the pendulum example, but there's a whole nother branch called electricity and magnetism. So there's one specific law that is called Faraday's law, and it includes something called Lenz's law. The combination of these allows us to see how this demo works. So here at this end, there is some magnets here. So these are strong neodymium magnets. And if I pass them through these red coils of copper wire that are insulated, and I do that slowly, nothing happens. Now, when the magnets pass through these coils, there's a magnetic field that's going into the coils. So when I do it this way, the magnetic field goes into the coils. And it sort of penetrates this cross-sectional area. So when that happens, Mother Nature does not like that to change. Mother Nature, if we have an area like this circle, if we have a magnetic field line going through that, Mother Nature does not like that. So what Mother Nature will do is develop a current in this copper such that we can generate a magnetic field that points in the opposite direction. So this depends on the speed or the time rate of change of this quantity called magnetic flux. So when a magnetic field crosses an area, that's called magnetic flux. So if we do that slowly and change that magnetic flux slowly, nothing happens. However, if we do it fast, well, now we have enough potential difference developed that we can actually light these LEDs here. So you can think about it as developing a potential, and that's what lights these LEDs. Now for this bigger example here that Jacqueline's going to show us, this is a very heavy 14-pound piece of copper, pure copper, and a very strong neodymium magnet. So what she's going to do is drop that through that piece of copper. Whoop, gotta catch it. I missed. But that did not just drop straight through, right? That took a very long time to go through. So what's actually happening there is as it goes through, there's a current circling this copper wire. Whenever we have a current in nature, that current generates a magnetic field. And that's what's happening here. As it drops down, the flux is changing. Mother Nature doesn't like that. Develops a current in the copper that opposes that magnetic field. And that's what slows it down, is the two opposing magnetic fields. So we drop this guy in there, it goes very slowly. Now, you can also demonstrate how you can control copper with this magnet through induction. So copper is not magnetic, but still, I can control it with this magnet. So again, this is the same idea. Whenever we have a current in this copper, and that current interacts with a magnetic field, it produces a magnetic force. And that's what you're seeing here. So the force on this copper is due to the current and the magnetic field interacting. So I can also pick this magnet up without touching it. All right. So same idea. All right. All right, so another branch of physics it's kind of tied with electricity and magnetism, is optics. So we have a couple optics experiments here. First one is these are little water-filled polymer balls. Florists use them to put plants in, keep the roots nice and wet. But there's nothing else except for those little hydrated spheres of polymer in here. If I take this laser, we can definitely see, don't blind Jackie here, that laser goes straight to my hand, right? However, we put that laser through here, it definitely does not hit my hand. It bends in many different directions. So basically when a laser light, not necessarily a laser light, but the natural light that we have, whenever it hits an interface, it bends, because different objects have different indices of refraction. So light travels differently in different types of materials. So when it hits this air and essentially water interface, it bends. And this is why when you look at a cup filled with water with a straw in it, it looks like the straw is bent, okay? Well, what happens, like I said, these guys are mostly all water. So take this, pour some water in here, what happens, now my laser light goes straight through. Okay, so it's passing through everything now. It's not bending because there's virtually no interface, because they both have the same index of refraction of water. So you might have noticed this guy off to the side. Okay, well behind this one, same type of gel film polymer spheres. You might notice there's something in there. So for $1 million, you probably could not tell me what that is. And again, the laser light definitely doesn't go through, it gets scattered. However, if we take one of these balls, sort of the same idea, it disappears when I put it in the water. Well, and we're gonna need that other one. Now you can clearly see the object that's hidden inside there. So that is my son's star toy. All right, so like I said, you saw this guy sitting up here, and this is actually vegetable oil that you can buy at your local grocery store. But what you didn't know is that while we were talking up here the whole time, this is just filled with Pyrex. So it turns out that Pyrex, and Jackie, could you get me that tub that all this stuff came in? So there is a ton of stuff in here. There's a whole nother beaker in here filled with vegetable oil. The point is the index of refraction of Pyrex and vegetable oil is exactly the same, even though they have a different color. So that's why when you stick the Pyrex into the vegetable oil, it's as if there's no interface. The light doesn't bend, doesn't know that there's an interface there. So that is a pretty cool optics experiment, and then we have one more experiment to do. Today we're going to talk about Vortex Rings. That's going to be one of our last demos that we do here. And Vortex Rings are a complicated phenomenon. There's things like friction, conservation of linear momentum, conservation of angular momentum, and there's so much rich physics we can talk about vortex rings with, but what we're going to do is show them today. So it's often hard to see these, so what we're going to do is show them today. And a vortex ring is basically a ring of air that's moving and rotating in on itself, and it's very stable for long distances and long periods of time. So what I want Jackie here to do, who's the president of the Society of Physics Students, I want her to give it her best shot from here to blow out that burning candle. Now I'm going to go more than 6 feet away from Jackie so that she can take her mask off and give this her all. Well, it flickered, but it did not go out. So now I'm going to try. But this time I'm going to use Vortex Rings. So I'm going to fill this with a little bit of smoke so that we can actually see this ring. My aim is terrible. There we go.